Hello everyone and welcome to the week number 2 lecture slide, and I'm going to divide the whole lecture into two parts. The first part is going to be about the uh, overview, the views and the projection, the orthogonal projection, the sizes and the dimensions, the section views and the drawing sheets. And then I'm going to have another video for the second part, which is going to be about the engineering design and the CAD. So the engineering drawing is going to be the first part we're going to start with. And here we are with the engineering drawings. Let's go to the engineering drawings. So now, a picture usually is worth of thousands of words. Now, how we can describe that? If I try to describe something for you, just orally, maybe it's going to be very hard to be done. Now, just imagine that you are sitting in the classroom, then I tell you how to go to, just how to go, okay, to a certain place. I can give you some what they call it, instructions on how to reach that place. It's going to be much better if I get to write down this instruction on the paper, or it's going to be even much easier if I get to make a map. So the map is going to be a picture. The same thing if I would try to describe a certain creature I saw. I can tell you, well, it's mixed between the lion and the cat. Well, lion and the cat, same thing, between the lion and the cow. So you will get confused. So which part is the cow? Which one part is going to be a lion? So it's going to be much easier for you if I get to sketch that. Okay, so that's what we mean by the picture is worth 1,000 words. So in engineering, a good drawing is worth even more than 1,000 words. It's going to be showing the dimensions, specifying the material size, and indicating the finished surfaces. Engineering drawings are important in conveying the useful information to other engineers and mechanics. So, the machinist. So, for example, once again, I will try to have a bar. So I'm going to tell the machinist, okay, now please make me a bar that's going to have three diameter sections. The first section is going to be 20 millimeters, the other one is going to be 30, the third one is going to be 40. But I didn't give him other dimensions, like for example, what the width of each one, what the length of each part, so what the surface finishing for that. So that's why we need to do engineering drawings, so we can argue if we're going to have a different dimensions from the one that we're looking for. So the engineering drawings will allow the readers to visualize what the proposed products will look like. Also, it's going to provide some information on the dimensions and the materials used to make the proposed product. Finally, it's provided views from the top, the side, and the front. So, what do you need to communicate from the engineering or the technical drawings? First, you need three-dimensional shape of a concept of the product. Second, the size and the dimensions of the concept three-dimensional shape. You will also need to be able to read the other technical drawings to determine what the three-dimensional objects other technologies are trying to communicate to you. This has led to standards ways of the communications. We have standard drawing sheets and line types, as well as a standard projection views to communicate the shape of the three-dimensional object. In general, in Australia, we're using the Australian standard, the AS 1100.101 for 1992, that tell us how to specify and interpret the engineering drawings. You should understand the basic rules for the engineering drawings, like for example, how to show the dimensions, how to specify the material size, and indicating the finished surfaces. You should know when to use the isometric views and finished surfaces. And you should also be familiar with the different types of the sectional views. You should have good understanding of the importance of engineering drawings in conveying the information to other engineers, machinists, and the assembly personnel. You should understand what is meant by the orthographic views, isometric drawings, and the sectional views. So, to understanding the solid objects, we have three-dimensional figures are referred to as the solids. Solids are bounded by the three surfaces that contain them. These surfaces can be one of the following four types: planar, single curved, double curved, and wrapped. Regardless of how complex a solid may be, it is composed of the combinations of these basic types of the surfaces. Every solid is going to have edges and vertices. The edges of the solid is formed where the two surfaces are going to be intersect. The edges are represented in the drawing by the visible or the hidden lines. The vertices, in general, the vertex, which can be plural or vertex, of the solid is formed where the three or more surfaces are going to be intersects. So you can see from this diagram that we can have the faces at the intersection of the two faces. We're going to have the edge. At the intersection of three faces, we're going to have the vertices. We can say that's going to be the corner. The points and the lines. The point is used to represent the location in the space but has no width, height, or depth. So actually the lines consists of multiple points. So the point is used to represent a location in the space but has no width, height, or depth. The line is used to drawings to represent the edges of the solid objects. The angles. The angle is formed by two intersecting lines. A common symbol for the angle is what we see here. The common manufacturing features we can have in general, and that's what we learned by using the SolidWorks earlier last week, was the fillet, the round, the counterbore, the countersink, the spot face, the boss, the lug, the flange, the chamfer, the nick, the keyway or the key seat, the knurl, and the bushing. So for the drawing and the sketches, the following are the important skills to keep in mind for the sketches and the drawings. First, we should have an accuracy. Second, the speed. Third, the legibility. And finally, is going to be the neatness. So in general, there is no drawing is useful unless it shows the information correctly for the accuracy. For the speed, the time is of course going to be money in the industry. To work smarter and learn to use the techniques to speed up your sketching and the CAD drawings while still producing the neat accurate results. For the legibility, the drawings is means of communicating with the others, so it must be clear and legible. Give attention to details and things that maybe seem picky and small as you are drawing may be as significant and save money or even lives when are going to be products to be built. Finally, for the neatness, if the drawing is going to be accurate and legible, it must be also clean. The system of the views is called multi-view projection. Each view provides a certain definite information. For example, a front view shows the true shape and size of the surface or the surfaces that are going to be parallel to the front of the object. For the isometric projection, or what we call also the simulated perspective, the isometric drawings look at first like the perspective drawing, but the lines do not converge. there are actually no vanishing points, and distant objects are going to be the same sizes as the nearby ones. The right angles in the isometric projection are usually going to be represented by 60-degree or 120-degree angles. For the oblique projection, similar to the isometric projection, it is also simulated perspective. The oblique projection, the side of the object is going to be facing you, is drawn as a square and accurate as much as we can. So that is with the right angle at 90 degree, and it is measurements proportional. The side not facing you are going to be distorted. The orthographic projections, flattened ones, view of the objects onto a sheet of the paper while retaining the correct proportions like the angles and the dimensions. The maps are example of the orthographic projections. Usually it's going to be a top view of the place. The trouble with the orthographic projection is that one view usually is not going to be enough. So the maps and the floor plans are exceptions where one top view is going to be often enough. So we continue with the orthogonal projection. The orthogonal means that the principal axes are going to be right angles to each other, and we can get a 2D view of objects. There are two types of the orthogonal projection, the first angle projection and the third angle projection. The standard for Australia is the third angle projection. Actually, I advise you to read more about that. Just make a basic research on the Google, and it will give you more details with more examples. However, again, simply going to only give you some example about here, or simple definition about the third angle projection. So the third angle projection will put the view from the right side of the object, on the right side of the front view. Okay, so you can see in these diagrams, and maybe I need to have laser here. Okay, so what you can see here, that this will be the front plane, and this will be the right plane, and this will be the top plane. So you can see here that we have the first, the second, the third, and the fourth about the angle projection. So this will be the third angle projection in the US. Front, what we said is that the view from the right side of the object on the right side of the front view. Here it is. Okay, and of course, what we are going to get as well is that the first angle projection, again, to put the view from the right side on the left of the front view, and that's what we can see on the other side. Okay, so this is the first angle projection, that the front, you can see that the right is going to be actually on the left, because we look at the things from that direction. Away from that, so the standard for Australia, as we mentioned, is going to be the third angle projection. For the 60 view system, the engineering drawings is going to be a multi-view projection that shows all the 6 sides of the objects. The 60 views are the front, the top, the right, the bottom, the left, and the rear view. The example we have here is from the civil engineering, but sometimes going to be used for the mechanical engineering as well, if the other 3 views going to give me a details that not can be identified by the 3-view projection. So how the views can be created? The 6 mutually perpendicular planes of the projection are used to create the 60 views. A surface is going to be projected onto the 2-dimensional plane, and the glass box is method in which the techniques is going to be used to create the orthographic projection. Now, why are the views going to be used? The views are used to clearly and economically convey all the needed information about the object. The views are used to create the three-dimensional object using the two-dimensional projections. The other consideration we have in the 60-view system is that the front view is usually going to be the one that shows the most of the features or the characteristics. So the example we can have here, the front view is going to be the front of the house, where we're going to have most of the dimensions, most of the details is going to be shown there. Not all the views are going to be necessarily used. Only the one that's going to have the details which is going to be unique by this view. The auxiliary views or the sections may be included to help to define and communicate the part. Dimensioning is used to indicate the size characteristics of the object itself. So in the concept of the glass box, you can simply put the object inside the box. You're going to take a look and, for example, sketch the view that you can see on this side. And then when you open it, you are going to have the 60 view going to be shown up to you. So it's a method in visualizing visualizing techniques that used to create the orthographic drawings of the object. It's involved the imagining and an object placed inside the grid box with the six sides. When we're going to open these sides, we're going to have the six projections. So if I get to have the glass box to be unfolded, as you can see here, I get to have the front view, top, bottom, left, right, and the rear one. Usually 3 regular views are going to be used, and that's what we call the glass box concept, and they are going to be views most of the frequently used one. So how does that work? Simply again to imagine that the object is going to be placed inside a clear box. Look at the object from each side of the box. Project onto the glass only what you can see from that side. And finally, unfold the box to reveal the 2D drawings of each orthographic view of the object. The sketch or drawing should be contain only the views needed to clearly and completely describe the object. Some objects can be fully described with one view or two views only. Like for example, you can see that the washer heat can be described by one view, which is going to be top view, and its thickness will be enough to describe what is the specification of this one. Okay, so just have a look. That's what I need to cut the washer, and I'm going to give it different thickness. Can be 1 millimeters, can be 5 millimeters. And the other object was going to be the real one. I can actually describe it with two views, which is going to be the top and the side view, or we call it the front view. So I can see it from the side, or the front view is going to look like an I letter, and from the top is going to tell me that there is a hole in the middle, and I know what the diameters are. Often, a single view supplemented by note or by lettered symbol is going to be enough. Like what we have here, this is the cross section, or how can I see a shaft from the side, and I think that we've done something similar to that in the lab last week. So we can see that this is the total length of the shaft, and we can see that different sections that have different diameters, and also we're going to have a thread for the distance of 38 millimeters with the specification of ME20 by times 0.5. That's the thread type, and this is the pitch value for the for that thread. So complex projection also can be applied. For example, we can have the isometric and prospective one. We can have the oblique type and the orthographic type. So prospective drawings look nicer when they're going to be used by an artist, but in general, the isometric, the oblique, and the multi-view drawings give more accurate information when used by technical drawings. So the isometric drawings shows the accurate dimensions but distorted angles. The oblique drawings give an accurate dimensions for one side only. And we talked about this one earlier. The orthographic one, which is going to be the multi-view, are going to be best choice for most technical drawings. Some terminology of the engineering drawings are going to be the drawing lines. You can see that we are going to have the dash one, continuous, and the center line. This shape usually going to be for a cross section, and you can have a different thickness for these lines. Also, we can use some letterings. We can use the measurement system. It's going to be either in inches or in millimeters. The scales, that's for example, this one is 1 to 10. Okay, this cube is 1/10 of the larger cube in a scale. And also we can have the title block where we're going to have the that will be the engineering drawings, and in title block we can put some details about who did that, why you did that, and what the name of the part. So to understanding the scales, 1 to 10, 200, that's mean 1 millimeter in the drawing is equal to 100 millimeters a real size. 2 to 1 means that 2 millimeters in the drawing is equal to 1 millimeter of the real size. Mainly we do that if we're going to have the scale of a very small parts. For example, let's say there's going to be a part of a microchip. So in that case, if we're going to make it as engineering drawings, we increase the scale instead of decrease the scale. So the line types and the lettering we have in this table 3.1 in the chapter 3 of the Australian Engineering Drawings Handbook, you can see that the type is given as A, B, C, D up to K, and the description of each one. So A is going to be just continuous thick line, while the B is going to be continuous thin line. The thick line to indicate the visible outlines, while for the thin one is going to be for the friction outlines, the dimension, the projection, and the hatching. So for example, again, to have a square shape, and I would like to know the length of one of the side, usually I get to put thin lines at both ends, extension of these two corners, and I put line between them to tell that the distance between this one to that one is equal to whatever the value is. Also, we can have a continuous thin freehand line, and on the part sectional boundaries lines or the terminates of the parts view, and for the short break lines. We can have a continuous thin ruled line with an intermittent zigzag shape, and that's to show the break on the adjacent members to which the components are going to be attached to. Thin dashed line, okay, to show the outlines of the hidden features, like for example, again, to have the cylinder going to have a hole. So to represent the hole, I'm going to put a dashed line showing that, okay, internally we're going to have some features. We have the medium dashed line, and we have the thin chain line, and we have the chain line, which is going to be thick, and then the thick at the ends, and it's going to be thin at the bottom with the change of direction, but thin elsewhere. We can have the thick chain line, and we can have the thin double dashed chain lines. So you can know what the usage of each one as described in that table that's available for you in the lecture slides. The letters are very common use in the engineering drawings, and you can see that how we can use it in drawings. A, continuous, means thick, used for the visible outlines, general details. B, continuous thin, is going to be this line is going to be half thickness of the A type, and used for the leaders, projection, and dimension lines. And hatching lines used to indicate the sectioning. The F dash line, thin, is going to be a line, is going to be half the thickness of the type A line, used for the hidden outlines, and the hidden outlines or the hidden details should only be shown on the drawings when their use is going to be necessary to understand the drawing. If the view has any hidden details shown, then all the hidden details on that view must be represented, and this can lead to a complicated, difficult to read drawing. The G chain thin, this type of the line is used for the center lines. The center line should be used to indicate the center of the holes and the centers of the symmetry objects or the features, and also the volt circles or the path of motion. So some of the basic form of the letters and the numbers are demonstrated in the figure 112. the height or the edge of the character pertaining to the particular sheet size is going to be stated in table 1.2 at the page 8. And also the characters should be spaced twice the letter line thickness or 1 millimeter, whichever is going to be greatest. Some of the general rules for the character usage. First, use the uppercase letters in most of the cases, except for the standards. For example, for kilogram, you should use the lowercase. Only use one style of the characters per drawing. Use a vertical character for the titles, drawings, and references, and avoid underlining. Characters should be kept clear of the lines unless they are essential to the drawing. The three types of the lines used in the orthographical views are: the solid line represent visible edges of the plane and the intersection of the two planes. For the hidden or the dashed line represent the edge of the plane and the extreme limits of the cylindrical hole inside the object, and the intersection of the two planes not visible from the direction you are looking for at. So the once again, the other type of the lines is going to be the center line, which represent the line of the symmetry, center of the holes, and the center of the cylinder. So now you can see here, we can have the center line, that's the center line, and this is the visual edge is going to be the thick line, and we have the cylindrical hole is going to be represented by the dashed line. Okay, so that will be the use of the three types of the lines in the orthographical view. So we're going to have this in-class exercise where you have to sketch this object, find the draw of the orthographic views, and I'm not going to show you the solution. You need to do it yourself. The freehand sketching, and we talked about this one in the week 1, and we did it actually on the whiteboard. So for the freehand sketching or sketch are going to be a helpful way to organize your thoughts and record ideas. They provide a thick, low-cost way to explore various solutions to design a problem so that it's going to have the best choices can be made. So it doesn't have to be always a full drawings at the beginning. You can simply just make the hand sketch yourself, put all the details, put some initial dimensions on it before you're going to go and make your final engineering drawings. It's very useful actually, it's very good practice that used by the engineer. Okay, another any-class exercise is going to be making a freehand sketch of the following two parts in 3D. So this is the part number 1 and this is the part number 2. Just have a look on them, make your inspections, and then try to make a 3D model for both. It's not that hard task, and we can work on that together. So every engineering drawing must include the following. First, we should have the dimensions. Second, the tolerances. Third, the materials from which the products will be made. And fourth is going to be finished surface marked. And finally, the other notes such as the part numbers. Two concepts need to be followed when specifying dimensions. Is going to be what is the size and what's the location. The basic dimensioning practice is going to be first dimension lines that provide information on the size of the object, and also the extension lines, that lines that are going to be extend from the point to which the dimensions or the location is going to be specified. Also, the lines are drawn parallel to each other with the dimension line placed between them. So the leaders are arrows that point to a circle or fillet for the purpose of specifying their size. The fillet around the edges of an object the size, the radius of the roundness must be specified. Information box will contain the name of the person who prepared the drawing, the title of the drawing, the date, the scale, and the sheet number and the drawing number. A well-dimensioned part will communicate the size and the location requirements for each features. The communication is the fundamental purpose of the dimensions. The parts are dimensioned based on two criteria. First, the basic sizes and locations of the features. Second, details of the construction for the manufacturing. So you can see, for example, in the four photos below, the first one is going to tell me the M1220 minimum thread to be full. So this will tell me, okay, now the hole is going to have 20 millimeter in diameter. It's going to have the full thread with the type of the M12 for the thread. From the top, you can see that once again, this will be MAT 1.56H. So it's going to give me the tolerances. It's going to give me what will be the diameter and what the type of the thread is. M18 by 1.5. That's for the pitch value, and this M18 is the type of the thread. 22 is going to be diameter, is going to be full thread, and so on. So the solid circle is going to be diameter of the hole, and the inside one is going to be the thread because it's going to be a little bit wider. So here we have the M12 by 1.256H. The 6H is tolerances, this is the pitch value, and this is the type of the thread. Now, some basic of dimensioning practice we have is, I think that we talked about this one earlier. This is the whole part. I'm going to first find a reference, and then I'm going to start to make the size from that. So now for this shape, it's going to be just a block with two holes. We're going to have the leaders, which is going to tell me what the size of this one. That's a leader line. This is a dimension line, which is going to have the two lines at the end, and we're going to have the two arrows line in between them, and the size will be written in the middle. This will be done for all the two sides. This line is going to be used to indicating where the center location are going to be, so we can tell what the location for the right circle from the right side and the left circle from the left side. So that's what we call the extension line. This is the center line, and this is the dimension line. That's further drawing. Once again, is going to have the same thing. This shape doesn't have it doesn't have any holes, so you can only have the projection lines are going to be used, and then we're going to have the dimension line to show what is the dimension from one point to another, and this will be indicated by the length of the line that we have on the drawing itself. Now, some of the steps of the dimensioning are going to be: first, dimension the angled face. So you can see that that's what we have, the angled face. This is going to have a slope. We're going to have the horizontal line, and we're going to show what the angle of that slope. Dimension the height, the width, and the length features. So that's what we have here. That's the width and the height and other length features. Locate the hole of the object, and using the horizontal and the vertical distances. So once again, we're going to identify that where's the center, and we can show where is the location of that center. Finally, we're going to have dimension the size of the hole, like what we have here. We put just the arrow, and we say this one again to have the phi of 0.5. That means diameter is going to be 0.5 inches. So some engineered product generally going to be consists of many parts, and in that case we're going to have an assembly process. So will everything fit correctly if the actual dimension of the machine parts is going to be off from the specified value or not? So obviously the thing is going to be not, because the mating parts should have a good accuracy and good tolerances. So we must specify the tolerance on your drawings regarding the machine parts dimensions. So every dimension we can give it a tolerance. So for this one, for example, we said that we have 2.5 centimeter plus minus 0.01 centimeters. So we're going to have the the chance to have the dimension to be either 25.1 or 2.51 or 2.49. So we give tolerances for the manufacturing process. The sectional views are used when the object have a complex interiors, have some details we need to show for the technician or the other engineers. So it reveals the inside of the object, and also this is created by making an imaginary cut through the object, and the direction of the side of the is going to be marked using the directional arrows. So for example, again, to make these directional arrows, okay, put a line and two arrows on the side. That means the view of the section AA is going to be shown from that side toward the inside of the paper. So it's going inside. Okay, that means I'm looking from that direction. That will be the cutting plane, and these are the details we have. Mainly it's going to show me how the holes are going to be represented inside the part. So based on how complex the inside of the object is, different methods are going to be used to show the sectional views. The common section types are going to be full section types, were created when the cutting plane passed through the object completely. We have the half sectional view, when it's going to be used for the symmetrical objects. Draw half of the object in a sectional view. Draw the other half of the object as an exterior view. Can show the interior and the exterior views of the object using one view. We have also the rotated section views, which used when the object has a uniform cross section with the shape that is going to be difficult to visualize. The section is going to be rotated by 90 degrees and shown in the plane of the view. The removed sections is another type similar to rotated section. Rotated section views are going to be removed from the view itself and shown adjacent to the view, and used for the objects with the variable cross sections, like what we have in this side. Okay, that's rotated side. So we just cut it apart of the section part of it, not the whole thing. That's the half sectional view. So we kept this part as it is, as the exterior, and that's the interior one. That's a full cross section, and this is the removed sectional view. So you can see that that's section AA, show the shape of the elliptical part here. The BB we show this one, and the CC because they are going to be different. So the removed sectional view is always going to be many cuts through the section are going to be shown, different one. Another any class exercise is we are going to be given this object, okay, shown on the right. Find the draw sectional view of the object as marked by the cutting plane. So we just need to find a solution for this one. So we're going to the drawing sheet. There are standards on almost everything. The first thing before we start the drawings is to ensure that our drawing sheet is of the proper standard. So we say once again that in Australia we're going to use the standard 1100 for 1992, and you can see from this diagram here we are going to have our engineering drawings. Here we are going to have the detail box. These are the different sizes of the papers, starting from the A7 up to A0. A0 is the largest, and the A7 is going to be the smallest. Usually the engineering drawing is going to be done on the A4 paper and go up. So you can see that each time the A4 is going to be half of the A3, the A2 is double of the A3, the A1 is double of the A2, and the A0 is going to be double of the A1. And also we do have the B type. You can see that actually the things has been shown on this diagram. So to communicate, we need to write down in this box who is drawing, why you are drawing that, when, the scale, and the reference number. So this information is going to be very useful to understand or to communicate with the reader of this drawing. Some standard sheet we have, as we mentioned earlier, there's the American National Society for the Standards, and we have the American Society for Mechanical Engineering Standards for the international and the US sheet sizes. Note that the drawing sheets is going to be given as a height and width, and most standard sheets are what's going to be called the landscape orientation. So you know we have the landscape and we have the portrait. So that's the size is going to be once again the height multiplied by the width. So the smallest is A4, the largest is going to be the A0. The international number zone of the zone is going to be given as 6, 6, 8, 12, and 16. International margin is going to be given for the drawing, so you can keep something from the size like 10 millimeters. For the standard and the US size is going to be in inches. The A4 is going to be 8.5 multiplied by 11 inch. Okay, so typical engineering drawings is showing here. That's the part. We show the isometric shape, and then we're going to put the three views. So you can see that this will be the front view, that's the side view, and that's the top view. And here we put all the information related to that drawing. To analyze the drawing, mechanical drawings are going to be constructed as per the Australian Standard 1100, and this allows for the accurate interpretations by those required to use the drawing. Therefore, it is important for the reader to be able to analyze the information recorded on the sheet. This is facilitated by the use of the standard drawing techniques to represent the common features. So this is a summary analysis for the part has been sketched, and you can see that we have actually a cross section for the part here. That's a bracket. Okay, we don't have to cut from this side because everything is obviously shown in the section AA, and this is the front. The front view is here, and this is the side view. So you can see that here we have all the details, including, well, it's actually been numbered and it's written on the other side. It's going to tell you exactly what are the part and the part dimensioning and the details of that part. That's a sample part, and we can do it actually for every the individual parts instead of the assembled part. So the next video is going to be about the engineering design and the CAD, and I'm going to record this one individually, and you can watch it after you finish with this one.